Good afternoon. We are talking of the empirical work on the Indian exchange rate today, and I would like to draw your attention to a spreadsheet here, Excel spreadsheet, where I have put the data of the US dollar Indian rupee exchange rate and the SDR Indian rupee exchange rate. The exchange rate data is from the RBI, Reserve Bank of India Handbook of Statistics. You can visit the RBI website to collect the data, and the other data on the other right hand side factors, which is the uh, pound sterling, Deutschmark, euro, Japanese yen exchange rate, differential inflation rate, differential real interest rates, the money supply, the GDPs, they are all from the World Bank World Development Indicators. So finally, the sheet that I would use is this, wherein these are the years, and these are the US dollar Indian rupee exchange rate. The first column, A column, is the SDR Indian rupee exchange rate. B, C, D are pound, euro, yen exchange rate. E and F are differential inflation rate, differential real interest rate. G is money supply here. H is the money supply in the foreign country. I is the GDP in India. J is the GDP in the US. So now I could either take it to eViews or I could take it to Stata. So let's take it to, if you want Stata, okay, eViews. So is 41 years data. So once you open eViews, it's easy. You go to work file, and you have to put annual data from 1971 to 2011, and you get this icon. Go to quick, edit series, and you paste the data. So series 10 will become my dependent variable, and series 1 to series 9 will be the set of explanatory variables. So go to quick and then estimate equations. So we will apply least squares, SER 10, C for the constant,
sorry, SER. Okay, so
that is the OLS results that I get. This is the R square that I get, 0.994, 99.4% of the variability in the dependent variable is explained by all these explanatory variables, which is on the higher side. Also the Durbin-Watson statistics is 1.44. So if you recall, if the Durbin-Watson statistics is nearing 0, there is an evidence of positive autocorrelation. So one has to take care of this Durbin-Watson statistics. And here are the results. Look at SER01, which is the pound rupee exchange rate. So it comes with a positive sign, and it's significant. The rule of the thumb is if the t values are greater than 2, then it has a significant impact. So if pound appreciates, the US dollar in terms of Indian rupee also appreciates. So pound has an impact, mark or German mark or euro has a negative sign. So if euro depreciates, then only US dollar appreciates, dollar in terms of Indian rupee. So there is an inverse relationship. Yen has a positive impact. 4 is differential inflation rate, it does not have any a significant impact because you can see the probability value is 0.80. Series 5, if you apply simple OLS, again differential real interest rates does not have a significant impact. But then 6 and 7, 6 is money supply, it has a significant impact on the Indian rupee, on the US dollar Indian rupee exchange rate. Excess supply of money, remember excess supply of money leads to reduction in savings, it is equivalent to excess demand for goods and securities, leads to balance of payment deficit. If there is a deficit and it is a flexible exchange rate, you will see a depreciation of Indian rupee or an appreciation of the US dollar. So, that is reflected here. The money supply in the foreign country does not have a significant impact, but 8 is the GDP of our country. Now, see it comes with a negative sign because remember higher the GDP, larger is the demand for money, more is the savings, lesser is the demand for goods and securities. There will be a balance of payment surplus leading to appreciation of Indian rupee or a depreciation of the US dollar. That is why you see a negative sign at SER 08. And then even GDP of the foreign country have an impact on the rupee, US dollar rupee exchange rates. So, this is the result that you get when you apply simple OLS, but in time series you have to be careful about two things, autocorrelation and about the unit root. So, when I checked for unit root, each of these variables had a unit root problem. That means the series is non-stationary. If the series is non-stationary at the levels, then you first check for co-integration. After differencing the series, if all are even, then you can have co-integration. If all of them are not of the same order, then you do VAR, vector autoregression. And in vector autoregression, what is more important is this impulse response and variance decomposition. That say for example, if the pound changes, how much impact will be there on the US dollar Indian rupee and in how many time periods, that can be checked through variance decomposition. So, if you give a shock to the system, how will the variables be affected after certain time periods? That is the information that you get from impulse response and variance decomposition. So, we will do that two things. First, let us apply the remedial measure. It is very simple. If you have to apply GLS, what you need to do is do AR1, and this is autoregressive 1. It is the first order autocorrelation coefficient, and here are the results. That is the remedial measure. This is GLS, OLS applied to the transformed model. What is the transformed model? You transform the original model in such a way that it starts obeying all the assumptions of the classical linear regression model. I can show you the econometrics of this, but see the set of results you get. Again 1, 2 and 3, pound, euro and yen have a significant impact on our exchange rates. This is the data from 71 to 2011, and then differential real interest rates have become a significant factor in explaining the Indian rupee exchange rate, and it comes with a positive sign. Now, one would have expected that if the interest rate goes up here, there will be more money coming in. If more money comes in, it leads to appreciation of Indian rupee or depreciation of the US dollar, but this is with a positive sign. Now, the reason that it comes with a positive sign is that differential interest rate is the lending rate minus deposit rate. It is not the deposit rate minus lending rate, it is the lending rate minus deposit rate. That is how it is defined, the real, and it is adjusted for inflation. That is why you see a positive thing. So, higher the real interest rate means lower the deposit rate, lower the deposit rate, lower is the money coming in, lower is the money coming in. So, you will not see an appreciation of the currency, you will see a depreciation of the Indian rupee or an appreciation of the US dollar. That this series, see 1, 2, 3, 4, 4 and this is 5, it is significant say at 10%, at 5% no, but at 10% yes, and 6, yeah, you are right, it is not significant at 5%, it is significant at 10%. So, these two factors that we talked about, inflation, differential interest rates, in Indian context it does not work. I mean marginally differential interest rates do. So, that may be one of the reasons when RBI, so it is not a good predictor. The good predictors for Indian rupee are the movement in the other exchange rates, our money supply, our GDP. Okay. That may be one of the reasons that RBI does not announce a pre-announced path for the Indian rupee. It does not say that we follow these parameters. Okay, only it talks about having orderly conditions in the foreign exchange market, no speculation, nothing of that sort, but it is not a crawling peg, it is a managed floating. Whenever there is a difficult situation in the foreign exchange market, it intervenes. That may be one of the reasons. And so, 7 and 8, 8 is our Indian GDP and it comes with a negative sign, and 9 is the GDP in the foreign country. And AR1, please recall, if it is a autoregressive structure of order 1, this is our model. How many? 10, 9. This is our model. This is the classical linear regression model, and this ut is rho ut minus 1 plus it, and this is working out to be 0.657. So, it is on the higher side. Remember, this rho is like the product movement correlation coefficient, it varies from -1 to +1, and you saw the Durbin-Watson was moving towards 0. It was 1.4, and after you have applied the remedial measure, Durbin-Watson has gone up to 1.60. And this AR roots, it's this rho for stability, this is less than 1. So, it works out to be 0.66. Remember, how do you do the remedial thing? You do yt minus 1, b1 plus b2, x2 t minus 1 plus b3, x3 t minus 1, and so bk xt minus 1 plus ut minus 1. Then you multiply it with rho. And then you do yt minus rho yt minus 1. So, you will get beta 1, 1 minus rho plus beta 2 x2 t minus rho times x2 t minus 1 . So, this is the transformation that you have done. You had this original model, you transformed it into this, and if you know rho, then you can apply OLS to this transformed model. So, this you apply OLS to the transformed model, because when you do ut minus rho ut minus 1, you get xit. Xit is white noise, expected value of xit is 0, variance of xit is sigma square, covariance is 0. So, ut minus rho ut minus 1 is xit. Earlier in this, ut was following an AR structure, now it is transformed, it is xit. So, you can apply OLS to the transformed model, and if rho is known, then you can simply apply OLS to this transformed model. That is GLS. Now, problem comes is rho is unknown, right. So, you have to get an estimate of rho. Once you put an estimate of rho, it is called the feasible generalized least squares, Zellener's feasible generalized least squares, because that omega matrix is an estimated one. So, do you recall the Cochran-Orkut procedure? So, that is this is the Cochran-Orkut, it is the feasible generalized Cochran-Orkut or the feasible generalized least squares. You estimate rho, right. When you estimate rho, there are two ways of doing it. You can start with taking rho as 0. When you take rho as 0, it is like applying regressing yt on all these explanatory variable, getting the regression, generating the residuals ET series, right. Now, regress ET on ET minus 1, and so this is step 1, take rho is 0, regress yt on all the explanatory variables, get the estimates, find out the residual series ET series. You have ET series, you have ET minus 1 series, regress ET on ET minus 1. That will be an estimate of rho. So, you get rho in step 2, then put it back here again, then regress new set of y variables on new set of x variables, generate the residuals ET series, regress ET on ET minus 1, get an estimate of rho, put it back here, keep doing this two-step iterative procedure, keep doing it till you find convergence in rhos. That converged value of rho and the estimates of alpha and beta are the feasible generalized least squares estimated. So, Stata does the Cochran-Orkut. eViews is little more enterprising. It does the nonlinear least squares. What is nonlinear least squares? If you had taken this here on the right hand side, so then if you had taken this on the right hand side, you would get yt is equal to rho yt minus 1 plus b1 1 minus rho plus b2 x2t minus b2 rho x2t minus 1 plus so on plus beta 9 x9t minus beta 9 rho xt minus 1 plus xit. You have less parameters, but you have more equations, more normal equations. So, if you apply OLS, you cannot get the unique estimates, because the number of unknowns are less than the number of normal equations. So, then what you do is you apply nonlinear least squares. Nonlinear least squares is like you start giving initial values for all the parameters and then you minimize the residual sum of squares. So, that is like trial and error. Start with the initial value, see whether the residual sum of squares are minimized or not, keep doing it, but that is not an easy way. So, you need an algorithm wherein you there should be a proper way of giving the initial values and what would be the next values and what will be the final values. So, nonlinear least squares is like you apply the Taylor's expansion to any function, right, and in that way you get an algorithm of how betas are related with each other. So, eViews with a click of mouse does nonlinear least squares. It was difficult in the 60s, 70s when you did not have computing, but now they have already have an inbuilt algorithm, different algorithm, Gauss-Newton, Newton-Raphson and so on. There are so many algorithms going on. So, it gives the estimates. So, the last point on this is that I will now take it to Stata to show you how this Cochrane-Orcutt procedure works and whether we get the same set of results that we are getting here from our nonlinear estimation, whether we get the same thing from the Cochrane-Orcutt, because Cochrane-Orcutt enterprising thing was that what he did was he just took this term on the left hand side and then he said you do not even have to apply nonlinear least squares, you apply OLS to this, but he had these two steps. Two steps were because one was how to get an estimate of rho and then second was the iteration procedure. Right. So, Cochrane-Orcutt or feasible generalized least squares is a two-step iterative procedure. So, I will quickly take this data set to Stata now. These are the results that I get by applying nonlinear least squares. I will just leave you with the command that you have to do. Next time if someone asks you that if you are working on time series, how do you take remedial measures? You take remedial measures by imposing this term AR1, that is all, and then you should know what you are doing, because what it does is that at the end it is giving you an estimate of rho, it is giving you an estimate of rho which is 0.657. So, you should know that this is the coefficient which is attached to yt minus 1, you should know it. SCR 01, so you have a constant, so this will be a constant, this is the constant that you get. So, this entire term is a constant, and if you know rho you can know B1, right. So, this constant is this B1, then beta 2 x2t, it will be SER 02, then for the coefficient which is attached to x2t minus 1, it is minus beta 2 rho x2t minus 1. Now, when you already have beta 2 and you know rho, you should be aware that this is the coefficient which is attached to x2t minus 1. Okay. So, again then we will have beta 3 x3t, then there will be a term which will be minus b3 rho x3t minus 1. Okay. So, this is not giving the complete picture, this is this only gives you this beta 2, beta 3, b1, you have to know about this equation. So, that is this. Now, unit root, again if you have this view, okay, so this is the series that you have, yeah, look at this series statistics unit root test SER 01. So, SER 01 unit root. Now, would you like to use augmented Dickey-Fuller? The first thing that you do is click on trend and intercept, test for unit root in levels, and the lag difference by default eViews gives it as 1. Otherwise, there are criterion to know what will be the lag difference. So, you click OK and this is the result that you get, minus 2.20. So, if the absolute value of this is less than the critical values, then there is a presence of unit root in the series. So, at levels this series is is non-stationary. Now, you go to view, there is unit root test again. Now, see the first difference and then click OK. Look at this, even after differencing it once, the absolute value is still less than the critical values. So, it has not become stationary even after differencing it once. So, then again go to view, do unit root, go to the second difference, click OK, and see now that it has become minus 4.70, take the absolute value, this is greater than this. So, this series is I2, the series 1 was pound rupee, it is I2. Now, you check for each of these, if all of them are of the same levels, are integrated of the same levels, then you can apply co-integration. If not, then you cannot apply co-integration, then you have to apply VAR. So, that is what we found, that the series some are I2, some are I1, some are I0. So, you end up doing VAR. And in VAR, now that I am in eViews, look at this quick, you have to put all the endogenous variables These are the VAR results, impulse response, you have to click into variance decomposition, and you need a table, so you click OK. Now, if you, because our interest is series 10, series 10 is the rupee dollar exchange rate. So, most of the variability in series 10 is explained by, now look at series 1, which was the pound rupee exchange rate, 34% of the variable in 10 time period is explained by series 1, euro explains 3.5%, Japanese yen 16%, differential inflation rate 0.66, differential interest rate 19, 6 money supply 4, money supply in the foreign 5, 8 is GDP in the miss. What was series 1? Let just hold on. Yeah, series 1, series 2, okay, series 5 and 6. Series 1 was pound, series 2 was euro mark, series 3 was Japanese yen, series 4 differential inflation rate, series 5 differential interest rate, series 6 money supply, series 7 money supply in the foreign country, 8 GDP, 9 GDP in the foreign country, 10 rupee dollar. Yeah, so 10, we are interested in 10. Yeah, so we are interested in the variance decomposition of series 10. Now, so series 9 1.78%. Now, here if you go read through VAR analysis, this ordering also matters. Okay, if I had put series 10 here and the others, it would have given me, it is possible that it gives me another set of results, right. So, ordering matters when you do VAR, but this is the result that you get. So, we had an impression when we started reading about Indian exchange rate that maybe that differential inflation rate, interest rates, the exchange, we were not very sure about whether how does pound have an impact. So, pound, euro, yen, they do have an impact on our Indian exchange rates. So, that is what you do when you do VAR, you do impulse response, and in impulse response, see the graphs that you would get. These will be the graphs that you get, say if you give a shock to the, if the pound changes abruptly, how will it have an impact on its own series and the other series. So you have to closely see this, and it comes with this colored line, so you can see the trend. So I haven't had a good look at it, just 8 or 9 days work. So I will have a look at all these impulse response and see how the other variables get impacted. So these are the results that I get. Quickly, if I take this data set to Stata, so I have already put the data. Stata, you go to time series and then you apply Price-Winston regression and look at this Cochran-Orkut transformation. There is this Cochran-Orkut transformation, and you click OK. Now see the iteration, this iteration, remember this row starts with 0. So you regress yt on the explanatory variables, then you generate the residuals, et on et minus 1, it does the iteration, keeps doing it till you find this convergence, right. And so, and here you are, see the results. Variable 1 was the pound, so it is significant. Again, euro has a negative impact, yen positive. Look at variable 5, which was differential real interest rate, now it's become significant. 6 was money supply, 7 was money supply in the foreign country, 8 was GDP in the home, 9 was GDP in the foreign. The Durbin-Watson statistics after transformed has gone up from 1.44 to 1.60. So the same set of results that we got when we applied nonlinear least squares, similar. So this is what you would get. You can consider this as a regression equation, you can forecast the values using this. But at the end, as I said, when you do time series, you have to check for unit root, and every variable has a unit root. So if you, this regression becomes invalid if you have a unit root problem. So then you have to end up doing either co-integration or VAR. So that is why for beginners, whenever I teach that econometric class, I say that you use the cross sectional data, because in time series you end up doing this. You have done the remedial measure, you have taken care of autocorrelation, but you haven't taken care of the unit root problem. So then you do the VAR analysis. Okay, I will end up here. Tomorrow I will be back on trade policy, but people who are working on the exchange rates now, you've taken the clue out of this. You put the data on the spreadsheet, you do the regression, then you do the remedial measures, and then probably you have to check for unit root, and this is what. So you can do it for any of the other exchange rate, Chinese renminbi or any other, and see the factors which have an impact. And then I can break this into different samples from 1971, that's the time when the Bretton Woods system broke, till 93, when we had our exchange rate where the RBI used to determine the exchange rate, and after 93 it was market determined. So intuitively it will be interesting to know whether the same set of factors are important after 93 and before 93, right. Then you can do some other transformation, you can take the logs on both sides. If you take the logs on both sides, left and the right hand side, you will get elasticities. Elasticity of output with respect to, output here is elasticity of the US dollar vis-a-vis the real interest rates and the other variables. The other thing is, in Stata you can also get standardized beta coefficients. Standardized beta coefficients will tell you which of the variables have more significant impact than the other variables. For example, just for say in the statistics, if I do time series Price-Winston and see the whether I can let me see if simple linear regression, yeah, normalized beta coefficients. It is like putting all variables on the same platform, right. You normalize the variables, because normalized variable has mean 0, variance 1. The beauty about regression is that even if you have variables in different units, you can establish a relationship, but sometimes you want to compare the performance of each of the explanatory variables which have a more significant impact. That in that case you have to normalize the variables, and then once you normalize it, look at these standardized beta. So from here it seems 1.14, this GDP of our home country has the most significant impact, because absolute value is 1.14, followed by the GDP of the foreign country, then the money supply. So this is a simple regression, you can show many things. So in India's case, it is like the GDP and the money supply which has a greater impact on our US dollar Indian rupee exchange rate. Because see, the pound is significant, but the absolute beta value is lower, 0.33. So this is significant, so it has a greater impact. So one can write a neat paper on all these results, then you can do VAR, you can write this 10-page paper, 11-page paper on this. You know what are the right hand side variables, you have a theoretical backing for each one of them, then you have the results, you know the VAR, it is a complete exercise. So I am looking forward, I have after 18th I will start writing. If you can come and supplement it, we can have a joint work where we can put it somewhere. That is how it works, otherwise you keep planning that we will do it, never happens. Okay, I will end up, thank you so much.